Welcome to the last lecture of CS 159, Data-Driven Algorithm Design. Today, it is a great treat to have Stephan Zheng to give the presentation. Stephan is a senior research scientist at Salesforce AI. Fun fact, he did his PhD right here at Caltech, where he was my very first PhD student. Now at Salesforce, he's been working on reinforcement learning and multi-agent systems, and also connections to applications to economics, such as mechanism design, which is the work that he'll be talking about today. Take it away, Stephan.
Thanks, Zheng. Thanks everyone for joining today. I hope you're all well and safe, and we live in challenging times. So I hope we all also take some time to reflect and listen and do our little part to try to make the world a better place. And today I'm really happy to tell you about this project I've been working off my team at Salesforce called the AI Economist, where we try to apply reinforcement learning for tax policy design. And the reason we've done this is that we've really thought about how we can use machine learning to improve the world in the future. And if we look around us, economic equality is one of the biggest issues of our time. And so we've seen that in the past 50 or so years, the incomes has grown very differently for different parts of the population, where in the US, the top 1%, as you can see, has seen their income grow many folds compared to the bottom 20%. And this is not just a US trend, it's actually also a global trend. And here, equality for today's purposes is going to be how much incomes differ between the workers in an economy, and productivity will be the sum total incomes of all individuals. And this is a worrying trend for various reasons, because it indicates lack of economic opportunity, health issues that are all very well documented. Now, if we ask ourselves how we can improve this, then this is actually really hard. Because if you look at traditional economics research, it often has a lack of data, or the models they use are way too simple. And in particular, it's really hard to experiment with economic policies in real life. You can't run two parallel versions of the US and see what happens in one versus the other. And in particular, this is true for taxes. They are the key government tools to improve equality in society, because you can use taxes to transfer wealth from the rich to the poor. But at the same time, the problem with taxes is that they can discourage work and therefore decrease productivity. And this essential trade-off is at the heart of the optimal tax problem. And in a cartoon on the left, you can see that in this trade-off, you can compare different ways of setting taxes. So the free market, US federal and SES, and AI economists all will set different tax rates, and they will give you different equality versus productivity trade-offs. And there's this so-called Pareto boundary, which is the theoretical point beyond which you can't improve one without decreasing the other. And our goal is, one, to get as close as possible to this Pareto boundary, and also perhaps control where on this boundary we might end up. But the canonical picture here is that every tax system might be inefficient and give you a different outcome. Now, what is this AI economist? As I mentioned, it's a way to use reinforcement learning to solve this tax problem. And more broadly speaking, one of the reasons we are so excited about it is that we want to have this simulation and data-driven solution to learn economic policies more broadly, and provide this tool for economists and governments to safely test and accelerate the design of economic policies. And we've seen that things like inequality, productivity are really global issues. We do hope that in the future, these kinds of tools can inform better policies that will improve the world for the better. Now, the underlying technology here is reinforcement learning, and I believe that this topic has come up a couple of times in this course, but for the sake of getting everyone on the same page, this is the canonical cartoon that I believe almost every talk on reinforcement learning will show you, is that this reinforcement learner agent is in this feedback loop where it observes the world state that we will denote by S, and then we have this policy model called pi that is trying to maximize its expected discounted reward over time by executing actions A that will affect the world. So in this loop, this model is going to execute actions, it's going to change the state, then it receives some reward and a new observation, and the loop goes around and around. And this has been successful in games like Go and StarCraft and so on. But what's also interesting is I just want to point out that reinforcement learning can be applied beyond those kinds of problems. And I believe the last lecture talked about chip design. You can also apply this technique to things like natural language processing, and this work is just getting started in that sense. Okay, now I just want to talk about some related work before we dive into our work, because there's a rich tradition of studying tax and also reinforcement learning. To first tell you a little bit about optimal tax theory, this is not an economics course, so I'll just give you a flavor of the work that has been done before. And when we look at the tax problem in 1927, this gentleman called Ramsey wrote work on what we can perceive as linear taxation. And his first studied this problem where we imagine that there's a planner that's deciding how much to tax the workers in society, and is trying to maximize a social welfare function subject to some set of economic constraints. And the key concept that he looked at was that you have to account for the fact that when I tax somebody, you might work less. So accounting for this response was key to this study that he did. And in 1971, he established in a body of work the subject of nonlinear taxation, where the amount of tax might depend in a nonlinear fashion on the state. And also, he introduced this idea that workers are not really the same. So he said, people have different skills, different education levels, and so that should be reflected in these models. And then in Saez from 2001, that's by far one of the most prominent works in optimal tax theory. He kind of had a blend of the first two, and he derives optimal nonlinear tax rates by using elasticity. So elasticity is this quantification of how much individuals respond to taxes. So the limitation in that work, though, is that he considered the static case where the economy doesn't really change and we're at some optimal point. And so there's no real dynamics where people might go to school, for instance, and increase their skill. But it is the easiest to implement and most prominent baseline. So we compare the result mainly to that work. And just on a point of having dynamic skills, there is this work called the dynamic public finance, where people have tried to sort of apply a control theoretic analysis to the idea of a dynamic economy, where, for instance, people might go to school and increase their skill and so on. But it remains very hard to explicitly solve these optimization problems quite in a similar fashion as reinforcement learning. It's often very hard to optimally derive or to derive the optimal policy in a mathematically exact closed form. Now, another feature of this work is that it's simulation-based. And in economics, there's a strand of work called agent-based modeling. And in agent-based modeling, people try to simulate agents and institutions that might interact through some prescribed rules. Now, the biggest limitation of that work is that they often don't use learning, and they often use very simple rule-based agent policies and institution policies. So these systems tend to be quite simplistic. And so there's some work there where people have looked at taxation, but again, the question is very often about the emergence of complex behavior if you have some simple rules on the individual workers that collectively then give rise to complex behavior that might reflect the real world in some sense. And thirdly, we use reinforcement learning, and in that particular subdomain, multi-agent reinforcement learning in recent years has been on the rise, where the central problem is this idea that if I'm learning and I'm in an environment with another agent that's learning, this gives rise to a non-stationary problem, because as agents are exploring, they're changing their policy. But the agents that are in my environment that are also changing their policy give rise to a non-stationary environment, because literally the world's constantly changing around me. This makes learning in multi-agent reinforcement learning extremely hard. Now, there's a number of papers that have tried to stabilize this type of instability. For instance, by modeling other agents. The idea is that if you understand how the other person is changing its policy, or what its policy even was, then you might have an easier time adjusting to their change. Or you can assume that you share some information. So if you tell me how you're going to change your behavior, then it is going to be easier for me to adapt to that. And another technique in that literature is something called reward shaping, and it's a more general reinforcement learning technique. But the idea is that if in some multi-agent problems there's a form of conflict, then it might be better if we share rewards, or if somebody is forcing us to share our rewards with each other. That then will motivate more cooperative behavior out of agents. And in some way, the way we can think about this AI economist is that it's actually learning how to shape and change the rewards of the individual agents, because you're taxing people, and so that the changes their payoff for their work. And then lastly, I'll mention that there has been some machine learning that has looked at economic problems, but in the setting of auctions. So our collaborator David Parks has a paper on learning optimal auctions with deep learning, and that's not using reinforcement learning, but instead it's trying to learn optimal mechanisms with data-driven methods. So that's a lot of previous work, but hopefully it gives you a sense for the context of our work. And I'll pause very briefly, and if there are any questions, then let me know.
Yeah, if you have questions, you can of course raise your hand or type your question into chat. I have maybe a quick question. Most of theoretically rigorous economics, which I think is most of economics, they assume some sort of optimality, right? I mean, in reinforcement learning, you basically assume that your agents are optimal, but there is no real guarantee. Is that something that's sort of okay in this field, or is that something that you view as sort of a significant hurdle that must be overcome before these two fields can merge more?
Yeah, that's a really good point, and I think that actually hits the nail on the head, because one of the things that people try to do in economics is say, what does the optimal situation look like? Everyone's optimized, has found the best behavior, like good Nash equilibrium, for instance, then what does it look like? And very often it's actually impossible to derive closed form policy models that tell you what the agent would actually do. And so there's this question of like, what might happen as I try to optimize my behavior, but maybe not quite get there for whatever reason. But it's a very, I would say, not a very well understood problem. It's not really how people think about the problem.
There's a follow-up question in chat. Have you thought about how this might connect to, I guess there's an area of economics called bounded rationality, where they assume the agents don't have infinite computational power. Have you thought about connections to that line of research?
Yeah, I've thought about it. It's not in this work, but bounded rationality is super important, especially if we move towards more realistic simulations. There's this thing called theory of mind and recursive induction. I forget the exact term, but the idea is that I think that you think that I think that you think, right? That's that problem. And this, you can imagine that this can only go on for so many hops before you just break down. And that is something that I would say people have studied in multi-agent reinforcement learning, for instance, but it's not something that is, again, completely understood how you can implement it in like a learning setting in the best way, I would argue. Yeah, that's a good question. Okay, so let me continue. So as I mentioned, the heart of this approach is to use an economic simulation. So here's a cartoon of what we've implemented. So you see a world here in which there's four AI agents. So you see these white eyes, and then every agent here can collect stone and wood. So in the bottom left, you can see that this dark blue agent is collecting wood and then building houses. And they can also earn money by building these houses. So every time, there's, depending on your skill, you get an amount of money in this world. And then you can also trade resources. So you can see that the orange agent manages to build a lot of houses, even though it's not actually collecting all that much by himself, but that's because he can buy those resources from the other agents. And then the AI economist who's invisible here also sets income taxes and subsidies on top of this system. Now, some details about these simulations that there's two resource types in this world, like wood and stone, and they can stochastically respawn on empty source tile. And in particular, there are several complex dynamics that can emerge if you make that respawn rate dependent on the neighborhood of that resource, and it can induce a so-called social dilemma. And there's also cost to collecting these resources. So your money doesn't come for free. You actually have to work for it in this world. And then trading here is implemented like a continuous double auction. So what that means is that it kind of works like a stock or commodity exchange. And for the details, you can see the paper. For sake of time, I won't talk about all the details there. And as I said, the agent can build, so you can use 1 unit of wood and stone to create a house. And again, the amount of money that you get for that depends on the skill of the agent. And what is important here is that we want to, for the simulation to be meaningful, it has to reflect economic behavior in some fashion. And in this case, the way we achieve that is by having this law of diminishing returns. What that means is that as agents work to make money and their skill determines how much money they get, every agent experiences a law of diminishing returns where their reward or their utility from working actually decreases as they make more and more money. And this is also a established behavior in real people, where above a certain income threshold, like you don't really become that much happier anymore as you make more money. So on the left, you can see, for instance, that if we look at the utility curve, so that's the middle row, and then the box on the right, you can see 4 of these log-like curves, and that's the utility. So you can see that as the agents, horizontally is the income, as they make more income, you see that their utility gradually increases, over a small amount, like a log. And what this means is that there's emergent specialization. So as I mentioned before, some agents will collect resources and then actually sell them to other agents that buy those resources and then use that to build houses. And that behavior is induced by the difference in skill. For some agents, it's profitable to build houses. For other agents, actually, it's more profitable to sell those resources to other agents. And it's this type of emergent economic behavior that tells you that this simulation is capturing some aspect of a real economy, because this is, features like specialization are things that people have observed in real life and that have been studied in the economics literature. Again, I'll pause here briefly for any questions about this. I'll leave the slide up for a second.
Yeah, question from the audience, yes.
I have 2 questions about this model. The first is that if we want to make have the tax for the agents, could the government, if they have the taxes, they could buy some public goods for the people, like in this model, can we have more river or more water? And the second question is, everyone is rational. It means that everyone is want to maximize their utility, and we do not consider the behavior economics. That is that right? Thank you.
Yeah, on the public services, that's a very good suggestion. It's not in this model, in our work here, the government sort of say only sets taxes. It doesn't buy resources which changes the world, although that would be really interesting for future work. On the second question, is this behavioral model of agents correct? And in that sense, this agent model of maximized utility, or this specific form of utility that I'll show you later, is simplistic because it's the standard classic economic model of an agent. But you're right that there are more sophisticated ways of trying to model human behavior, behavioral models, where people might not be, for instance, like maximizing a single utility, but maybe multiple utilities and so on. But that's not in our work. But again, that would be really interesting to include for the future.
There's a question in chat. Have people ever explored the idea of implementing rules like these in an actual game with human players and see if the human behavior matches expectations from simulated behavior from RL agents?
We'll see an example of this. You'll see an example of this later. For more generally in the economics literature, certainly people have done behavioral experiments where people play games or trade and so on. I think that for this level of complexity that we have, it's not really been done. But you can look, for instance, at Colin Cameron's work where he compared cooperation between people and then compared it to compare cooperation between monkeys. So yeah, there's some, but maybe not as for complex games like this, perhaps. But I don't know all the literature. But hope that answers the question. Okay, so now that we've seen this economic simulation, let's talk about how we do reinforcement learning in this setting. And again, to put ourselves on the same page, what we've used in this work is something called on-policy model-free reinforcement learning. And in this flavor of reinforcement learning, we have this parametric policy model, pi and theta are the model weights. And this model is going to compute a probability distribution over actions A given some state S. Now, the canonical way in which reinforcement learning works is that first you collect some data. That means that we've seen that feedback loop where the agent observes some state and establishes some actions and then gets some rewards and so on. And the way that it gets data can really be done in two ways. One is exploration, where the policy is going to try to use new actions. That means that it typically has a high entry policy and just tries something new. And then on the other hand, there's things like exploitation, where instead you use known good actions. So good actions where you've seen high reward, for instance, as a result in the past, and then you try to do more of that. So once we have that trajectory data, then we can train on that. And to do that, you compute a gradient. So you take the gradient of the expected discounted reward, and you can derive that in general, this looks something like this formula on the right, where the gradient is basically going to change the log odds of the actions that increase this objective function psi. And this psi, we can think of it as a surrogate objective for the expected discounted reward. So the number of things that you can put in here, like just the total future reward, but there are better choices like the advantage function or TD residuals, because in general, this expectation cannot be computed fully, but you actually have to estimate this somehow. And then for those purposes, sometimes, or but almost all cases, advantage functions are actually better suited because they lead to lower variance in your estimator for this expectation value. And then you just repeat this process. So what is the actual optimization for the individual agents and the planner? Well, as I mentioned before, every agent has a skill, and let's call that skill N for the IF agent. And as we saw, there's a number of action types. So agents can build, they can move around, they can collect resources, and every agent will perform some amount of labor that we denote by L. And then there's also taxes, capital T here. And these taxes are going to depend on the state of the system. And also the tax rate is called tau. This is standard econ notation. But altogether, this gives you the so-called post-tax income, denoted by X, where X is just how much you worked times how much skill you have. That gives you amount of money. And then we subtract some amount of tax from that. And this tax, again, is going to be determined by the social planner. But for the agent, it's a state-dependent function, or just a scalar. Now, the utility that we are using in this work is this sort of power law, where you take this post-tax income and you raise it to some power, 1 minus eta, and then we subtract the labor linearly like this. And that leads to these curves on the right, where you can see in orange, green, and blue, for different choices of this eta, for different choices of skill, not eta. So for different choices of skill, so for different choices of skill, you can see how the utility behaves. So we have a situation here where you work a certain number of hours, and we assume that you can only build houses. And then the only free variable here is then skill, also for fixed eta. And then for low, medium, high skill, you can see that the optimal amount of hours worked changes for every agent, but it changes in a nonlinear fashion. Now, the agents then maximize their discounted sum of rewards. And then in this case, we'll define the reward, the instantaneous reward at time t, as just the increase in total utility. So X and L here are total cumulative amount of money and labor that you've performed. And R is then the increase in utility that you experience at time t. Now, as I mentioned, there's also this government or social planner. And the social planner is going to set taxes. And the way it does it is in a similar fashion as agents. It's going to optimize some expected discounted reward. But in this case, the reward is the increase in some social welfare objective. And the way we define it in this work is that it's equality times productivity. Now, equality is defined through the Gini index. So the Gini index is this normalized sum of differences between the incomes between all the agents in this economy. And productivity, as I said before, is just the sum of the incomes, xi. Now, the reason we choose equality times productivity is that if we think back at this free-to-boundary cartoon, equality times productivity is a function that will increase, both as we go towards the free-to-boundary, basically. Now, the benefit of reinforcement learning is that we can actually choose many objectives to put in here. So we don't have to choose equality times productivity, but you could imagine that things like sustainability or social mobility or helping middle class, anything that can be quantified can be given to the planner as an objective. And so that's a really nice thing. And this flexibility of the reinforcement learning framework gives a large scope for the kinds of problems that you might be able to study in the future. And another feature of this setup is that it's akin to what's called a Stackelberg game, in the sense that in the way that we've set up our problem, the planner moves first, and then the agents can respond to that. That means in this case that the planner first executes some taxes or sets some tax rates, and then the agents get that information, and they can then choose their action to move around or build or sell their resources. So we have this situation, there's two entities learning, or two types of entities learning, this government policy, and then a collection of agents, each with their own policy and their own utility function. Now, this leads to this concept in multi-agent learning or game theory and a number of other fields, which is called the solution concept. And the question is, if I give you a problem with multiple entities that are all trying to optimize for their own objective, then what is the subset of optimal policies for each agent in your system? Now, a solution concept is a formal way of just defining a subset of all possible agent policies that we define as good. So what does good mean? For instance, at the optimal set of policies, you might not want any agent to unilaterally deviate and change its behavior. So if everyone else wouldn't change, then you don't want to change. So and there's many instances of these types of solution concepts. So in game theory, there's the Nash equilibrium. So this is very classic. And in markets, if you read about supply and demand, then there's something called the competitive Walrasian equilibrium. And again, this is a very high level description, but you can roughly think of it as the idea that demand meets supply in an efficient market. And again, this is a very old concept, but it has this this quality that it basically describes the solution concepts in this microeconomic theory. And then thirdly, as an example that you might be familiar with, is from auction theory, where you can ask, what's the best way of selling a painting for a given price, and where every buyer can tell the auctioneer how much they're willing to pay for this painting. And Vickery and Clarkson Groves, they basically have studied this problem, and then there's this concept called the second price auction, where the idea is that everyone says how much they're willing to pay for it, and the highest bidder wins, but it actually he or she pays the second price that was bid. And it turns out that this incentivizes everyone to tell the truth about how much they're willing to pay for this painting. So the theoretical analysis of all these equilibria, they've studied the existence and uniqueness and the characteristics of these solutions a lot. But as Zheng also asked about before, it's actually very hard to characterize what happens if you're not at this optimal point of the problem. And particularly in our sequential setting, it's very hard to actually compute these equilibria. And so again, the learning approach to this is that agents will use this data that they collect from the environment to try to learn to get as close as possible to their optimal policy. But yeah, like they might not get there, right? So in all of this, the important thing is that the reward function is always fixed. So in all the work that I described before, typically the reward function never changes. Now, in a related strand of research called mechanism design, we actually ask the inverse question. And we ask, how can we define rewards and rules of auctions, for instance, that will lead to equilibria that are quote unquote nice? For instance, everyone tells the truth about how they really feel about a painting. But again, this is really hard to actually solve in closed form. And in fact, like in 2007, Nobel Prize in Economics was awarded to the three gentlemen on the right for studying this problem. Again, it's very hard to actually derive optimal mechanisms. And this AI economist, in that sense, because it's learning to change the taxes, it's actually learning how to change the reward function for these agents as they're learning. And so one interpretation of this is that this AI economist is actually learning what the best mechanism looks like for its objective function, the social welfare function. And another analogy that might help you here to understand this is that if we think about generative adversarial networks, this is a technique that has been used to train neural networks to generate images. Generative adversarial networks use a discriminator model that basically learns to separate real from fake images. And the way it does that is also by changing the objective function for the generator network. So there's this analogy there as well that you can see that a lot of these works, they have some similarity. So I'll just pause there again if there's any questions about this this concept. So let me continue. So now let's actually look at the tax systems that we implement here. So we mimic the US federal income tax system. And I'm not sure if everyone pays taxes. I'm not sure how much you pay attention to that. It's actually almost tax season now. But the way it works is that as you earn money, the money gets divided into buckets, and then you pay a different tax rate in every bucket of your income. So on the right, you can see the US federal tax income from 2018. You can see that as you make more money, the higher buckets get taxed at a higher rate. So what our models are going to do is to predict like what these rates should be for every bucket. So here's our model that's going to predict these tax rates. So this diagram shows you what the flow of information is in our economic simulation. So this is a quite complicated graph, so let me try to unpack this. So in the middle, you can see all the different types of state information that exists in this world. So on the left, you can see that there's a spatial geometry that every agent can see, or at least a part of it. So for instance, in this red circle, you can see that this red agent can only see part of the world around itself. And this map is public, so you can see other agents around you. And also what's public is the set of tax rates that apply that period, and also what the prices are of resources in the market. Then there's also a semi-private state where the agent can see how much resources it owns, how many uses of wood and stone it has. And this is also visible to the planner. So that's why it's semi-private. And then there's also truly private information, like such as the labor and skill, that only the agent can see. And this is, again, like very important. The idea in economic theory is that we can actually observe how good you are at something, at least not directly. We can only observe it by proxy, like testing you or you doing exams. Now, the planner then is this deep neural network, which uses a convolutional neural network to do pattern matching on the spatial information, and also uses a fully connected network to look at the public state and the semi-private information. And then it combines all of this and then predicts 7 numbers, because there's 7 tax brackets. And then those are the planner actions. And then at the bottom, you can see the agent model. And then every agent, you can see that like the agent can see all the public information and also the private information that applies to that particular agent. And the model in structure looks pretty similar. And then that agent is going to predict probabilities for every action type: moving, building, and trading. Now, I already mentioned that in this setup, there's actually 2 entities that are learning. There's agents, and then there's the planner. And both of these entities are using reinforcement learning to learn. And that's actually a really hard reinforcement learning problem, because it's 2-level. As the agents are optimizing their own reward, expected reward, at the same time that reward is being changed by the social planner on the outside. So you can see in this cartoon here what that looks like. So in the inner loop, which is this red dotted line, you can see the agents, and the agents are observing the world, and then they're executing actions in this world. And on the outside, this social planner is looking at all the publicly available information about society, and then has its own social welfare function, and then adjusts taxes based on that. And what is hard here, again, is that because this reward function is constantly changing, because the taxes are constantly changing, as these agents are using reinforcement learning, they're constantly seeing their reward function change over time. So another way of saying that is that your post-tax income for the same amount of work might change over time. So this year, I might get paid 50% as much as I was last year. So in particular, that means that any decision I would make that I thought was optimal last year might not be actually optimal this year, right? So this gives you a very, in principle, it could be very unstable, this back and forth between the planner and the agents. And we found that in order to make these agents and the planner jointly converge to a sensible solution, we had to try a lot of things, first of all. And we discovered that there's a number of things that actually work. And the first thing is that you have to do 2-phase training. It means that like first you train the agent policy models from scratch, but you don't apply any taxes to them. And we do this for about 30 to 50 million steps. So steps means an environment transition for a single agent. And then in the second phase, you then take those agent models and then you turn on some taxes and you resume training. And so you can turn on the AI Economist, or you can turn on some other tax model, and then you then let everyone learn. The second technique that we use is curriculum learning. So in the first phase, you actually have to turn on the cost for working slowly. So in the beginning, at the very beginning, money is free. Like you don't, like there's work doesn't really exist. And then at the end of that first phase, the full labor cost has been annulled to 100%. And in phase two, the planner also annuls its tax. So in the beginning, it doesn't set 100% tax on everyone, but you have to start with 10% tax and 20% tax. And the idea is that this is a smoother way of deforming the reward function over time. This helps with stability. And the third thing is entry regularization, and this is very, very commonly used. So entry regularization means that you try to keep the entropy of the policy relatively high for some amount of time. And the general benefit of this, is that you prevent policies from prematurely converging to perhaps a suboptimal solution. So another way of thinking about that is that it promotes exploration for these policies. But because you apply entry regularization to both the agents and the planner, you essentially are giving both these models more time to adapt to each other's changing behavior. It sort of ameliorates the changes that you see in the policies. And again, this helps with stability in this two-level reinforcement learning setting.
I have a quick question. So, naively, perhaps let's say an economist who is thinking about this type of problem might say, well, we just pick a tax law and then we'll run the agents to convergence, look at the utility or the social welfare or whatever the global utility, and then pick another tax law and then restart the whole process all over again. So, really treat this two-phase training as a very decoupled or subroutine, like nested for loop style of training, rather than this intermixed. I think I know the answer, but could you comment on why you would not want to do that?
Yeah, it's really inefficient. First of all, it takes 30 to 50 million steps or even more, hundreds of millions of steps. And there are many tax policies, right? I mean, there's uncountably many tax policies, if you will. So it's not really, well, then even if you wanted to do that, then you have to start talking about which tax policies do you pick, right? Which ones do you compare? And really the reinforcement learning approach is that you just trust your gradients, right? The gradients will tell you which tax policy to try next instead of manually trying to define some sort of sampling policies in the tax space. Yeah. Any other questions about this before I go to the results? If not, then let's look at some numbers. So for all the theory, now let's see what
actually
there's
a question. There's a question. Yes, please.
Okay.
Hi, I have a general question. So in this, you assume that each of the agents are acting independently, but how does this model handle businesses or, for example, when a group of agents would be paying taxes together or situations like that?
So you're asking what happens if a group of agents colludes to pay taxes? Is that the question?
Yes.
Sorry.
Yes.
Yeah, so there's no collusion in that sense that we enforce on agents. So they can't, at least they cannot explicitly give money to each other, if that's maybe what you mean. That maybe I'm very I'm very nice and I see that Yisung has to pay a lot of tax, and somehow I'm like, okay, let me help Yisung out, let me give him a loan or something like that. Like we don't really have that here. So yeah.
I think also part of the question is about what actions the environment allows. So for example, I think another way to ask that question is there are legally enforceable contracts where people, like share some sort of risk or do some sort of shared work together.
Yeah, I I think it's a really interesting question. I mean, it's not in these slides, but there are I mean, there is emergent collusion that you can observe in some simulations. It's something that it's not in the slides, but we have observed that in certain settings, you can see that, for instance, if two agents are sharing a monopoly on a certain resource, so let's say you have 10 agents and 2 agents can have all the stone and nobody else can, then the agents can actually learn to do price collusion. So they have like a cartel, like where they artificially keep the price high. So it's not really like tax alliances or something like that, but it's more about emergent, price setting, if you will. So that could happen. Yeah. But again, it's not something that we explicitly allow these agents to do. It's rather an interesting emergent phenomenon that agents can learn to do.
Yeah, from that perspective, you can. I think if you think about companies, I think it makes sense to think of each individual agent in this simulation as a company. Like the collection of individual people to work in a company has some sort of legality to it that's not in this environment. And so different companies, of course, engage in price collusion. So yeah, I think that's sort of the abstraction that makes sense to me.
Right. Yeah. I mean, and this is a really deep topic, actually. And in actually economics, there's a difference in how workers and firms are treated, in the sense that their objectives are actually different. Because companies have to make profit, and workers, they get a different treatment, basically, in that economics literature. But yeah, for anyone who's interested in economics. Okay, so let me talk about results. Now, the main thing here that we want to compare is society better off between different tax models? So here you can see a comparison between the free market and the AI Economist. So on the left, we can see this pie chart, and this pie chart, the size of it indicates the productivity in society. So the pie grows, there's more money that's being earned by everyone. And then this coloring shows you how wealth is distributed in society. You can see that the dark blue agent here gets about 2/3 of the wealth. And then if you multiply equality and productivity, you get to about 1,200 something. And on the right, you can see what happens when you use the taxes that the AI Economist discovers. And you see that equality times productivity is much higher. It actually gets to 1,700. And you see that equality is better, because the dark blue agent gets roughly half of the pie in that world. And this improvement actually is statistically significant, or if you do many repetitions of the experiment, you can see that the AI Economist improves over 16% over the other baselines. So the blue baseline is a SAS model, which I'll discuss in a little bit. The purple model is the US federal tax scheme that we've seen before. And then the pink curve here is the free market, where there are no taxes at all. And you can also look at the productivity. So again, this is sort of a sanity check. You see that as we turn on taxes, productivity always drops, because again, taxes will lower the incentive to work in society. But at the same time, the equality improves. So you can see that all free tax models do improve equality over this pink free market equality. And if you do reinforcement learning, then you'll probably be very familiar with these types of curves. So here we can see how during training over many millions of training samples, you can see how the objective of in this case, a social planner is changing. And every curve here has a shadow around it. That's because you have to repeat these experiments for multiple random seeds. And you can look at the green curve first. So that's the AI Economist. And you can see that there's some instability in the beginning, but then over time it learns how to improve equality times productivity to a much better level than the other free curves here. And in particular, you can see that the free market and the US federal tax here, they don't show a lot of instability. And that's because their tax system is not really changing during training. But instead, the blue and the green lines, they do have taxes on the change. That means that you can see a bigger dynamic range and more dynamic behavior during training. And these trends are much worse if you don't use the tricks that I just described a few slides ago. And in the same way, you can look at the productivity and equality, which show you the same, tell you the same story.
There's a question in chat. On the previous slide, why is the economy different in the free market scenario? Shouldn't it always be the same?
The taxes there are no taxes at all, but the agents can still have to go from a random policy to a set of optimal behaviors. So that's what's happening. Are there any other questions? Okay. Now let me tell you briefly about the SAS model, because it is, as I said, it is one of the most prominent tax models out there. And what this tax model does, is actually optimizing for a linear social welfare function. So it takes a weighted average of all the agent utilities in this world. And what it does, it then defines the optimal tax rates, tau, in the middle here, as this ratio of 1 minus capital G divided by 1 minus capital G plus alpha times E. Now, this capital G is in pseudo-inverse cumulative of what's called the social welfare weights. So the social welfare weights, G here, are how much every agent contributes to a change in the social welfare as you change their income. And alpha is a weight of incomes, normalized weight here. And then E is the important thing. E is the elasticity of an agent. So the elasticity is defined as this ratio on the bottom, dz over z divided by d of y minus tau over 1 minus tau. So what this means, the way to read this is that the derivative of income with respect to taxes tells you how much I would change my income, or how much I would choose to not work or work extra as taxes change. And then dividing that by z and 1 minus tau gives you the normalized version of that. And this is like the central thing. So worlds with, let's say, elasticity 0 mean that I'm completely insensitive to any change. Whereas if it's a very big number, then I'm very sensitive. So like, if you change 1% in taxes, then I would maybe stop working altogether in an extreme case. And for normal real people, fun fact is that this E, depending on how you want to measure it, tends to be somewhere between 1 and 3 for free real for the US economy. Now, the way you estimate this SAS tax rate in this model is that you basically turn this elasticity into this linear form. So you can see that the log incomes versus log tax rates is actually a solution to this equation here. And then you can use the data that you collect during learning to estimate these parameters in this linear function using linear regression. So from that, you get this estimate for the elasticity from which you can compute the SAS tax rates that are being predicted. And there are a few things that have to be adapted, because this tax formula applies to a static economy in the original formulation. So what we did here is to have an episodic adaptation, because in this episode, we have 10 tax years. That means that an episode is 1,000 steps, and then 1 year is 100 times steps in this simulation. And then every 100 steps, some taxes are being changed and applied to these agents, and so on. Now, if you look at the actual tax rates that the AI Economist sets, it's actually different from the other systems. So in purple here is the US federal tax scheme, and it's progressive. And then the SAS tax formula in this case leads to a regressive schedule. So that means that as income goes up, tax rates go down. But instead, the AI economist finds, on average, this very different schedule that you can see in the bottom in green. In particular, it's goes up and down. So it has higher tax rates generally for lower incomes, then lower tax rates in the middle, and then high tax rates again in the top. And as I said, there are 10 tax years. So this is an average over time, but this trend is consistent. Now, what is a bit strange perhaps is that like the lower incomes actually gets taxed higher in this scheme. But the thing is that this system actually leads to higher subsidies for them as well, because there's more productivity. And so that there's more productivity compared to other tax systems, except for the free market. Now, what that means is that effectively the subsidies that agents get are actually higher under the AI economist. And the way that works is that the government collects all this tax money, and then every year that money gets distributed evenly across all the agents. So just to reiterate that, like tax rates are higher in the lower bracket, but in the end, the net subsidy that these agents receive is actually higher. So on the right here, you can see that the green subsidies here, their negative taxes, are actually better on average than under the other tax models.
There's a question in chat. Are the brackets exactly the same? So there's sort of two possible actions. One is setting the tax rate, and one is setting the bracket locations. So the bracket locations are kept constant here.
Yes, yeah, exactly, yeah. All the brackets are constant, only the rate change. Okay. Now, one really interesting feature is that these AI agents are smart, right? They use reinforcement learning to try to optimize their utility function. And in particular, it turns out that they can actually learn all kinds of interesting task-gating strategies. That means that over time, they can strategically choose when to work a lot and when to work less. And overall, they can find out that some of these strategies can actually lead to a lower average effective tax rate. So on the right, you can see that this green policy will alternate between high and low incomes over 10 tax years. And if you compare that to a situation where in the gray line, you're doing the same thing every year, you actually pay less tax over 10 years than, or if you're smart about it, you will pay less tax. And this works because in a regressive schedule, or in a schedule where there's a lower rate at higher incomes, it's actually favorable to save up your labor, so to say, for 1 year, because then you can profit from the lower rates in higher brackets. And what's important is that all the baselines and a lot of the classic economic literature doesn't actually account for these kinds of temporal strategies, because again, in a SAS model, the economy is stationary. Agents would always do the same. So you don't have that richness of strategic behavior that can appear in our setting. And what's sort of encouraging about this is that our social planner, our government model, can actually do well, even though these agents can be strategic. And this is really encouraging. So somebody asked about what happens with real people. So we also asked ourselves what happens if you actually put real people in the simulation. So we developed this web interface that you can see on the left here. And we went on Mechanical Turk and we asked people to control the agents. And the setting here is zero-shot transfer. That means that we took a model that we found during training with AI agents and then applied that to the situation with real people without retuning or anything like that. Now, the reason this is interesting is that ideally you would need as little fine-tuning as possible. And in particular, because for economic systems, as I mentioned, it's really hard to get data and so on. So model calibration in particular would be really hard in the real world. So the better the zero-shot transfer learning is, the more promising it is for the future. And we know that real people are very different from AI agents. This is exactly true for our system as well. And What we found is that actually there's a different solution that the AI economist has found that's more shaped like a camelback that you see in the bottom here, that actually turns out to work really well. And this solution here was found by using a low entropy, relatively low entropy regularization versus high entropy regularization. So high entropy regularization led to this pattern we saw before. Low entropy regularization led to this more camelback shaped strategy. So in AI experiments, this strategy does perform worse than the strategy I showed you before, but it turns out this one is more robust to this in a zero-shot transfer setting. I actually don't have video clips here of what people do. I believe maybe in extra slides, but people do behave very differently from very rational agents. And what happens in particular is that people are much more adversarial, it turns out, and they immediately start to block other people in this world. And in particular, that means that there's a higher variance in productivity, right? So instead of trying to collect resources and not really bother each other, people think that I should just like put you in a corner and keep you there, and that might be better for you. So in particular, if you look at the results, you can still see a trend in this equality times productivity, but you can see that the noise level is quite high actually for those experiments. Another thing that I'll add here as well is that we did have to simplify the simulation in some ways. So for instance, the agents couldn't trade because people have a really hard time doing multiple tasks at the same time. So the human study, there's a bunch of details here that again, for time's sake, I will leave it to you to read the paper, and you can see what we've done there. But it's actually quite interesting how people behave. So here's another metric that we looked at to do more analysis, and we also looked at this objective called inverse income weighted average social welfare, where we took this objective that the SAS model used and used this weights here that are the inverse incomes of agents. And what that means is that this social welfare function will weight the poor people more, right? Because it's the weights are inverse income. And it turns out that under this objective, this model also does really well. You can see that there's a better performance on it for the AI economist compared to all the other baselines. But in particular, you can see that the variance under this metric is lower because it weights the incomes in a different way. And this is another proof point for us to verify that we're doing something right with the AI economist.
So there's a question in chat about why does it make sense to have very low tax rates at the highest brackets? Could it be an artifact of some property of the simulation, such as 4 players? It might incentivize collusion and so on and so forth.
Now let me go back to this picture here. That's actually a really good question. I'll say that in general, it's extremely hard to do some form of causal inference or post hoc. I guess everything is post hoc rationalization of what might be happening here. One way to interpret this is that low tax rates might incentivize people to work harder because they can profit from the lower tax rates. You get more bang for your labor, if you will, for higher for those higher tax buckets. So one way of interpreting is that the social planner can use low tax rates to incentivize workers to work more. The second point that was raised about number of agents is that you can see that this dip here on the left is kind of unnatural. And in some sense, you can say that that might be because there are only 4 agents. Because very roughly speaking, because there's only 4 agents and they have like a certain skill, you can roughly think of this world as having 2 types of agents, like very low skilled and very high skilled agents. And for both these categories, you might incentivize them in a different way. So for instance, you might think that the lower skilled agents are incentivized by the social planner to make income between 9 and 39. And then for the higher skill agents, you might incentivize them to make income between 160 and 510. Yeah.
I see. So this maybe is as much an artifact of the number of agents as it is the assumed skill distribution of the population.
Yes. In particular, I would say that this dip on the left here is a sign of that.
Yeah. Okay.
It doesn't mean that low taxes are a bad idea, but it sort of elucidates the mechanism that, again, you're trying to incentivize people to work as much as possible in some sense so that it maximizes social welfare. And so this dynamic here is likely the way that the planner learns that it can motivate the learning agents to work more.
Yeah. But what about collusion? Could they like pool their wealth, and so one pays the high income bracket, which is low, and the other pays the low income bracket, which is also low? Is that allowed on the rules?
Again, I think that would work if you can directly exchange money, right? If somehow you have a shared bank account, but we don't have that here. The only way that agents can actually get money from one to another is through trading. And trading is not unlimited. Like it's limited by the amount of resources that are available in the world.
I think this maybe begs an interesting question, which maybe is more future work, which is, what are the most complicated simulations that economists do run? Both in terms of trying to model things as realistically as possible, and in terms of things where they can actually guarantee, say something about optimality versus, what are the opportunities that you think reinforcement learning can add to that? So you already mentioned temporal effects, which is something that reinforcement learning can offer that it may be hard to model in more traditional simulation settings.
Yeah, that's a really good broad question. In fact, like I mentioned agent-based modeling. So in fact, the U.S. Treasury and other government or semi-government organizations, they do use a blend of agent-based modeling and traditional economic models and fit them to data. I would say that, well, then this is I think an open research question, but the idea that you can at scale compare different tax policies and be efficient about how you compare things is something that they don't do. And in fact, like the biggest question here is very often is like, how do agents respond to a change in tax, right? So if I have a static model of the economy and I change the tax, then doing that, modeling that response is extremely hard. But that's actually what's essential to a lot of these models, right? Like the elasticity, for instance, it tells you how people would respond. And then by assuming optimality, you're assuming that you're at this fixed point, right? But very often we're not at that fixed point. And so reinforcement learning could offer you a way to understand that process better. Like how do people respond to a change in tax policy and vice versa? Okay, so I think we have about 10 minutes left. So am I correct? Okay. So let's talk about the future. So we've seen that this approach here is novel, and we hope that it can lead to a better way of developing social economic policies in the future. Economists typically fit models to real world data, and then getting that data is actually extremely expensive. It costs a lot of time. It's very hard to actually do this work in real life. A colleague of mine actually spent a number of years analyzing the impact of tax policies in India. So he spent about 2 years, I think, collecting data. So it's very time consuming, it's very expensive. And if we could build more realistic economic simulations and couple that to these kind of learning approaches, then hopefully we can more quickly analyze the impact of economic policies and how they change human behavior or behavior in general. And also, hopefully we can transfer the AI models that we've trained in the simulation to the real world in the future. And in particular, that means that there's a lot of new challenges for machine learning and AI. in particular using these tools for social welfare instead of zero-sum games and adversarial games. So there's two broad buckets of research that are very important. The first one is, if we want to enable this objective study of the impact of economic policies on real economies, we have to make better simulations. We have to improve their fidelity. And that also means that we have to incorporate real world data. So that might mean, for instance, that we collect more data on how people respond to certain incentives or in certain situations. And secondly, there are a lot of requirements that we would have for real economic policies around robustness and transparency. One aspect of robustness is value alignment. So we've seen that the social planner can have different objectives. It can optimize for equality and productivity, but also maybe host other objectives. And so the question is, how do you actually translate the set of qualities that we would like to have in society? And this is a broad public discussion. How do you actually translate that into a reward function in the right way? That's an unsolved problem. And the second question is around transparency. So if I double your tax rate, surely you would want to know why. But right now, explainability and especially for deep learning, is still a very big topic that's, again, not quite well understood. But in the future, we would like to have that. And how we can explain economic policy in the best way is also a huge research opportunity. Now, finally, I'll mention that with any technology, there's benefits and risks. And in this case, we've done our own ethics analysis of this work. And one of the potential risks in the future is that if we do use real world data, there's a risk of bias. For instance, if certain groups are underrepresented in that data, then your economic simulation will be biased. That's something that you have to be really careful about. And secondly, there is a potential in this work to do individualized taxation. So far, the models have showed you the tax is applied equally in the same way to everyone. But there's nothing in principle that prevents you from making these taxes personalized to every individual. And because that's possible, there should be a public discussion whether or not we actually want that, or whether that should be done or not, and how you can actually check that somebody who's implementing this, some governments who might implement this, how you can actually detect that. That's another risk that we have to really think carefully about. And we did consult with some researchers outside of Salesforce to review these risks, and all of that you can find in the paper. So I'll close out with mentioning that this is really a team effort. So I'm very fortunate to work with a group of great people. And in particular, they're not all Salesforce people, but we also worked with David Parks from Harvard, who is leading the economics and computer science research group there. Now, if you want more information, there are a bunch of resources that you can look at. There's a paper on the archive. There's also a blog post. The press that covered this work in a couple of places, so you can take a look there as well. There's a cute video that we made for this. That's it has these cute graphics on the right. And we are working on an open source version of our economic simulation, as well as a bunch of research projects that we would love to work on with the broader public, because we do think that this direction of research has a lot of potential, but it's going to take a lot of people, and not just machine learning people, but also economists and public policy people to actually drive this research. There's a lot of potential here, but as you can see and appreciate, perhaps there's also a lot of public debate that will have to happen in the future around the use or the correct use of this type of technology. But we are working on making that stuff open source, and I'd love to work with some of you as well if you're interested on this type of research. So you can always reach out to me if you're interested. So here's some references. I'm not sure if we're going to share these slides, but there are a lot of papers that are in either tax theory here or multi-agent reinforcement learning that you can take a look at. And with that, I'll thank you all for listening. And yeah, if there are any other questions, please let me know.
Great. Thank you for that presentation. It was really, really insightful. The slides are on the course website for anyone who's interested in downloading a copy. If there are any questions, we have a few minutes for any more questions. I'll just start with one. I imagine that you limited the simulation to 4 agents partially for computational reasons. Do you have a sense of how the computational challenges scale as you increase the number of agents?
Yeah, there's 2 sides to that. One is how fast can you simulate a world with, let's say, 1 million agents, right? What sacrifices are you making in terms of what features you have in a world versus how fast it is to run? So part of that is an engineering challenge, but the other part of that is also a really interesting research question, because you can ask for the best sim to real performance. What features in the environment should I have and what features are not so important? On the training side, the learning side, again, it's partly a question of engineering. So, there's several parties, we work on that. Parts like DeepMind, OpenAI have done a lot of work on scaling up multi-agent reinforcement learning from an engineering perspective, but also from a sample efficiency perspective, it's still very challenging. The scaling is, especially in a multi-agent setting, it's actually quite challenging, I would say. If you look at the sample complexity, right, for even something like Dota 2, for instance, you have to spend millions of compute time, millions of dollars of worth of compute time. You have to have, billions or trillions of samples basically to train 5 agents, right, to learn something as complicated as Dota. So I would say that there's also a lot of room for improvement in the algorithms that we use. And again, things like understanding how other agents change their behavior in response to your behavior is one direction that people have looked at, but I would say is still unsolved. So yeah, I think there are multiple dimensions to the problem, but the scaling still, I would say it's not quite good.
Yeah. The other question I have, it's somewhat generic, is I imagine you've gotten a lot of feedback or given this talk to economists. And I guess there's academic economists and then there's policy-facing economists. What has been their feedback about sort of the biggest things that are missing, or the highest priority things to add to this type of environment?
In their opinion.
Yeah, in their opinion, yeah.
So far, we haven't had a lot of feedback on the choice of the environment, in the sense that so far we haven't really gotten the feedback that the environment is too simple, perhaps. Because economists, they typically study economic systems that are actually more simpler than what we do, right? Mm-hmm. So the feedback has been mostly on, for instance, like the shape of the tax curve. Is that something that we could understand or understand qualitatively? So I think there's 2 points of feedback. One is this schedule that you found had the low tax rate in a lower bucket, for lower incomes, for instance. That is something that might be an artifact of a small number of agents. I think that's one of the responses we got, and that's something that's understandable. The second question is around like the dynamism of the social planner. So the social planner can actually change its tax rate every year, and so some of the feedback we got. We actually spoke with Thomas Piketty, who's a very prominent economist, actually. So he gave the feedback that in practice, we don't really see taxes change as rapidly or as dramatically, perhaps, as you might see in your reinforcement learning framework. And so why is that? And so there's a question more about implementability, I guess, is this actually feasible to do in the real world? But I would say that so far the feedback has been positive skepticism, let's say, like inviting for more research.
Sounds good. I guess we're out of time. Thanks again, Stephan, for this
I have one
Oh,
question.
one question. Go ahead.
Okay, so my question is, how did you go? It's about your trajectory. How did you go from your PhD research to working in mechanism design, economics, social policy? And when you signed up to work at Salesforce, did you think that you're going to be working on that?
Wow, yeah, that's a good question. So I learned one lesson from Yisong, which I'm not sure if he's okay with sharing that.
You can share it.
So he once told me that when you make decisions in life, you should use this bandit approach, where you look at where the highest potential payoff is, right? Mean plus uncertainty in the payoff of the bandit arm. So I took a little bit of that approach to my research. So I started out with actually studying cooperation and multi-agent reinforcement learning. And organically, that turned into the question of what are the right incentives for that? And then there was work on reward shaping, as I said, right? Like where people manually define certain agent rewards and try to change them to induce cooperation, but it was mostly done manually. But then we asked, well, can we do this in a dynamic way without setting this manually? Because that's, doing manually is not the machine learning way, right? So then we landed on dynamic incentives. And from there, we realized that's actually what economists have been studying. And then we realized, oh, economists actually don't use reinforcement learning. Why don't we try to do, more broadly speaking, analyze what the impacts of economic policies and how we can change economic policies using reinforcement learning. So it's an organic process. And I think at every turn in that fork of the road, I always looked at, things that people haven't done, but maybe should be doing, right? And I think that's really what Yisung's philosophy is, that he imparted on me, one of the things I've learned. So maybe that answers the question.
Any other questions?
Did you study mechanism design before that, like in any formal way, or it was all like organic, one thing led to another?
I took a course once on operations research for a long time ago, but it was the only exposure I had to mechanism design. But I do think I was exposed to it but by reading multi-agent reinforcement literature, for instance. It is something that has appeared a couple times in that literature. Yeah. So.
Great. Well, thank you, Stephan, for this very, very insightful talk and closing it out with imparting some great life lessons. Thanks again for everyone who's been tuning into the course, both here at Caltech and more broadly. I hope you always all enjoy this lecture series. Thanks again, Stephan.
Thanks so much, and stay healthy and stay safe, and let's try to make the world a better place.